All right, so let's go to number 26. And now we actually are going to be evaluating the integral. So number 26 says use the definition to find an expression for the area under the curve y equals x cubed from 0 to 1 as a limit. Okay, so instructions are important. They want us to use the definition that we just used before to find the area as a limit. Okay. All right, well, let's draw a picture. So remember the graph of x cubed, something like this. Okay, so we're going to find Rn of this interval. Okay, so we're going to be using the right endpoint to figure out the squares. All right, so this is what we're doing. And then as a limit, we're going to let's see, we have 1, 2, 3, 4, 5, 6, 7 rectangles. We're going to let the number of rectangles go off to infinity. Okay, and then according to the definition, what that looks like, is something like this. That's your definition 2. But R sub n is the sum of all the areas of these rectangles. So area of rectangle is the base times the height. So that's the definition we're dealing with, okay? And we know a lot of this. We know f, our function, it's x cubed. Our starting point is 0, which is phenomenal. Let's figure out delta x. Remember, delta x is b minus a. So the distance of that interval is 1 minus 0, b minus a, over n. All right, so it's going to be 1 over n. So this is what we're looking at. So we're going to be looking at the limit as n goes off to infinity of y equals 1 to n. Delta x, we said, was 1 over n. And now the function a is 0, and delta x is 1 over n. Okay, so something like that. So we have to evaluate then this limit. Okay, our input is essentially I over n, and our function is cubing the input, so x cubed. So we're going to be looking at I over n cubed. Okay. So let's clean it up. Cleaning things up, it's always a little bit easier to see how everything's behaving. It also looks nicer. So distribute the cube, so I cubed, n cubed. And then n times n cubed is n to the 4th. So I cubed over n to the 4th. Okay, so here's a little shortcut we're going to use often, and I'll explain it in 2 different ways. The only thing affected when we're doing this sum is the I. All right, so this n to the 4th, because it doesn't have an I in it, it's behaving like a constant. And it's going to be in every single term. So let me use a different color. If we were to extend this, so this is our thought bubble, expand this, let's see, I starts at 1, so it's going to be 1 cubed over n to the 4th. That's what summation notation means. I'm just expanding it. And then I equals 2. Then I equals 3. I equals 4, etc., all the way up to our starting point. It's telling us to stop at n. So n cubed over n to the 4th. And so in all of the terms, we have this n to the fourth. And so if something's in all of the terms, we can factor it out. So that's what we're going to do. That's equivalent to us moving it outside the summation sign. Okay, and now to really see it, so we just kind of did a mini proof. We can write this 1, 2, 3, da, 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 and that's summation notation. We're starting at 1, we're going all the way up to n, and the function is I cubed. All right, so this is our giant thought bubble. So moral of the story, if one of the factors in our summation argument does not contain an I, we can move it to the outside, right? So we kind of have a little shortcut, and we'll use that a couple times. So just kind of store that one. So where does that leave us? That leaves us here. So continuing, all right, A, we have the limit still as n goes to infinity, and we just simplified that next part like this. We have 1 over n to the fourth times the sum of I equals 1 to n I cubed. Okay? All right, so that kind of takes part of that first part. We express the area under the curve as a limit. Done and done. That's what we did. But look at 26 part B. We have a formula for the sum of cubes. Okay? We have the formula for the sum of cubes. Essentially, we have this. The sum of cubes, which is what this is, it's 1 cubed plus 2 cubed plus 3 cubed all the way up to n cubed. It's the sum of cubes. We have a formula, and it's this. It's n times n plus 1 over 2 all squared. All right, so we can actually now evaluate the limit by making that substitution. Okay, so now we have this. That area is the limit as n goes off to infinity of 1 over n to the fourth. And we're going to come in and substitute the sum of cubes. Just like that. And now it's time to simplify the heck out of this. All right, and eventually, now that we got rid of the summation, we know how to take limits at infinity. So that's exactly what we're going to do. We're going to take a limit at infinity after we've simplified everything. Okay, so what can we do to simplify? Well, we do inside the parentheses first. So I'm just going to do a little side work, so I don't have to keep writing the limit over and over again. So distribute that n. And then if we square that, so n squared plus n times n squared plus n, I like to use a squared plus 2ab. So if this was a and this was b, right? All squared. A little trip down memory lane. Let me do it in a different color for those of you that are feeling a little bit more confident. A plus b is a squared plus 2ab plus b squared. Okay, so n squared squared plus 2ab plus b squared. Okay, and I'm going to put that in the numerator. Okay, I just said the numerator squared was n to the fourth plus 2n cubed plus n squared. And on the bottom, 2 squared is 4. Okay? And we can clean it up a bit. Let's see, I see a common factor. If we, well, I mean, we don't really have to factor it out. It's just, we could factor it out. Sometimes math, we can go different paths and end up in the same place. So if you want, notice that we can factor out an n squared in the top. And we can cancel that with the n to the fourth. but we don't necessarily have to. We can just start evaluating this right here. Do you remember how we evaluate limits at infinity, what our strategy is? We divide out by the highest power in the denominator. Isn't that nice? Now we've built up all of these skills and now we can use them. Okay, so let's divide out each term by n to the fourth. All right, so n to the fourth cancels, so we have 1 plus, let's see, this is going to be 2 over n. That's going to be plus 1 over n squared. And then the bottom, that's going to cancel the 4. And now as n goes to infinity, we know that 2 over infinity is 0. 1 over infinity is 0. So what are we left with? 1/4. And that's our solution. So we're saying then, this is the exact area. It's not an estimate or anything like that. It's the exact area. We have infinitely many triangles, and it turns out that this area, let's try to highlight it exactly, is equal to 1/4. It's bananas, right? It's a bananas calculation. So right now, it's crazy to calculate that area as a limit. We are going to be learning shortcuts, okay? So, but it is important to just notice what the instructions say. If it says calculate the area using the limit definition, this is the process you have to use. Okay, so great. Now that we know how to calculate rather tediously the area under a curve, let's talk about the applications, or some of the applications of the area under the curve. All right, remember with the derivative, the big application was the derivative was the rate of change. So let's figure out what the applications of the area under the curve is, okay? So we know, let's go back to algebra. We can find the distance traveled when we know two pieces of information. When we know the velocity, back in the day, it's really the average velocity, right? And we know the time. Because we have this very simple formula that distance is equal to velocity times time. Right? Think if you're going 60 miles per hour, that's the velocity. For 2 hours, 60 times 2 is 120 miles. All right, so we can find the distance. So for us in calculus, it's not the average velocity, it's the instantaneous velocity. Because we have that velocity function that gives us the instantaneous velocity. So we can find the distance traveled when we know the instantaneous velocity. Okay, so that's going to be an application. How does that deal with area under the curve? Well, if we have our velocity function, so we have time versus velocity, right? And then here is our function, the function of time, and it's the velocity. Well, I made my interval very big. Let's see if I can fix that a little bit. This is time. Okay, so we have A to B, and these represent times. And we can create our T rectangles. Right? We have our n intervals, excuse me, not T rectangles, n rectangles. All right, and let's just take a look at this first rectangle. The base is time, right? The amount of time that's passed. So the base is time. And now what's the height? Well, the height is the value of the function, but what is the function? Velocity. So the height of each of these rectangles is going to be the velocity. And so when we're talking about the area, we're going to figure that out. It's going to be the time times velocity. And what is that? Well, velocity times time is distance. So each area of all these rectangles represents the distance traveled. So let me write that down. So the area of the rectangle is, I shouldn't say equals, it's an approximation still because the rectangles are relatively big. So it's approximately the distance traveled over that time interval. Okay, so the area under the velocity curve seems like it represents the distance traveled because of how our rectangles are set up. So to find the exact distance, what do we have to do to those rectangles? We have to have infinitely many. So let's let our n go off towards infinity. And so then we have the limit as n goes to infinity, and we're going to sum up all of these rectangles, or I should say the area of the rectangle, so area of the base times f of t sub I, and then this is the total distance traveled over that time interval. And it's fun because we can figure out the total distance traveled when all we know is the velocity function. We don't know s, the position function. Okay, so an application then of this, let's kind of summarize what we're talking about. It's the distance. We need our fancy pen for this statement. The distance, s of t, right? That's our s function, the position function. The distance traveled is the area under the curve, because that's what this function is, right? That's the area under the curve. The distance traveled is the area under the curve of the velocity function. Over a time interval. Okay, so that's one of our applications of area under the curve.